Hi, in this video we'll solve the following problem. So suppose there is a three consumers, two goods, pure exchange economy. Utility function of individual one is 2x1 plus y1. Utility function of individual two is x2 plus 2y2. And utility function of individual three is quasi-linear, which is x3 plus 2 root y3. Total endowment of both x and y is 3 units each. And we want to show that the allocation x1 y1 x2 y2 x3 y3 equal to 1 0 0 1 2 2 is Pareto efficient. So x1 y1 is 1 0, x2 y2 is 0 1, and x3 y3 is 2 2. Okay, so the way we are going to proceed and show this is we'll construct alpha 1 alpha 2 and alpha 3 such that this allocation solves this maximization problem, which is weighted sum of utilities of the three individuals. It maximizes the weighted sum of utilities of the three individuals, subject to the constraint that we pick an allocation from the feasible set. Okay, so of course constraint is that we have to pick a feasible allocation that maximizes the weighted sum of utilities. Okay, so this particular problem, the way we are going to approach and solve this is basically we can split it into two problems, because if you see this is uh, separable, in the sense that we can write x's separately and y separately, and we can write it as a sum of two problems. One is that we are choosing x1 x2 x3, subject to the constraint that x1 plus x2 plus x3 is 3. We are choosing x1 x2 x3 in such a way that we are maximizing 2 alpha 1 x1 plus alpha 2 x2 plus alpha 3 x3. And we can, and this is the separate problem, which is the second part of the problem, which is basically we are choosing y1 y2 y3 in such a way that y1 plus y2 plus y3 is 3, and we want to maximize alpha 1 y1 plus alpha 2 into 2 y2 plus alpha 3 2 root y3. Okay, so this is the objective. This is how we are choosing y. So we want to construct alpha 1 alpha 2 alpha 3 such that 1 0 2, x1 equal to 1, x2 equal to 0, x2 equal to 2 solves this problem, and 0 1 2, y1 equal to 0, y2 equal to 1, and y3 equal to 2 solves this problem. Okay, so let's just see what kind of restrictions, what kind of conditions on alpha 1 and alpha 2 and alpha 3 are required so that we exactly get this as a solution. Okay, now we want x1 to be 1, x2 to be 0, and x3 to be 2. So for this, it must be the case that 2 alpha 1 must be equal to alpha 3, so that you are indifferent between choosing any amount of x1 and x3, and alpha 2 must be smaller than both 2 alpha 1 as well as alpha 3. So basically, this, for this to be the solution, it must be the case that 2 alpha 1 must be equal to alpha 3, which must be greater than or equal to alpha 2. Okay, so this is the first requirement if you just look at this particular problem. And here we want y1 to be 0, y2 to be 1. So y1 is 0, y2 is 1, and y3 is 2. So in this case, because we want y1 to be 0 and y2 to be 1, this gives us that 2 alpha 2 must be greater than or equal to alpha 1. And if you look at this, so the partial derivative of this objective with respect to y2 because y2 and y3 are both positive, so and the in the constraint, we have the coefficients of y2 and y3 as 1, so it's a linear constraint. So it must be the case that partial derivative of the objective with respect to y2, which is 2 alpha 2, must be equal to the partial derivative of the objective with respect to y3 at the optimum, okay, which means alpha 3 by root y3. So these two must be equal at the optimum, and since we are looking at this as the optimal value or optimal choice, okay, so it must be the case that 2 alpha 2 must be equal to alpha 3 by square root of 2. Okay, so this gives us these set of inequalities. Okay, so 2 alpha 2 must be equal to alpha 3 by square root of 2. So we just need to construct or basically figure out possible values of alpha 1, alpha 2, alpha 3, so that this is a solution to these two problems, and therefore this allocation is a solution to this problem. So in fact, it turns out that any alpha 1, alpha 2, alpha 3 that respects these two set of inequalities will give you these set of equalities, and inequalities will be acceptable. Okay, so let's figure that out. Okay, so if you see, we can actually write this as, we can reduce this set in the following manner. We can just write it as 2 alpha 1 equals alpha 3, and this alpha 3 will be equal to 2 root 2 alpha 2. Okay, so we can just write it like this, and then just verify that this term is actually greater than or equal to alpha 2. So that's true. Okay, because 2 root 2 alpha 2 is greater than or equal to alpha 2. So clearly these two must be greater than or equal to alpha 2. So that's going to come for free. This inequality will be automatically satisfied, and this inequality will also be automatically satisfied, because 2 alpha 2 must be, because 2 root 2 alpha 2 is greater than or equal to 2 alpha is 2 root 2 alpha 2 is equal to 2 alpha 1. So root 2 alpha 2 is equal to alpha 1. Okay, so that means, if I multiply both sides, I'll get 2 alpha 2 is equal to root 2 alpha 1. Okay, so 2 alpha 2 is equal to root 2 alpha 1, and therefore this inequality also holds, because 2 alpha 2 is greater than or equal to alpha 1. Okay, because 2 alpha 2 is actually equal to root 2 alpha 1, so therefore it is 2 alpha 2 is equal to root 2 alpha 1, and therefore it is greater than or equal to alpha 1. So if we can just, so these two inequalities are just going to come for free. If we just, so basically the problem reduces to finding alpha 1, alpha 2, alpha 3 that satisfies these equalities, and now you can choose any alpha 1, alpha 2, alpha 3 positive, such that these three equalities, these three are equal, and so one possibility is we can take alpha 2 to equal root 2. Okay, so if alpha 2 is root 2, then alpha 3 is 4. Okay, so if alpha 2 is root 2, then alpha 3 is 4, and if alpha 3 is 4, then alpha 1 is 2. So this is one possible choice of alpha 1, alpha 2, alpha 3, which If we use these alphas, and maximize the weighted sum of utilities, the solution will be this allocation. And since it's a solution to a problem like this, therefore it is Pareto efficient. Okay, so that's it. That's a proof. Thank you.